Thank you for inviting me to speak with you. Today I'm going to talk to you a little bit about how to try to extend aquifer lifespans, and this will be done through a case study of the HighPlains aquifer in the United States of America. Before I discuss that, though, I would like to congratulate the Hydrogeology and Water Resources program here at the University of Costa Rica on its 25th year anniversary. I am most familiar of the efforts of Marco and Ingrid, but it's certainly a very impressive interdisciplinary program that incorporates law, engineering, psychology, geology, and geophysics. And I think having such an interdisciplinary group is key to actually solving some of the big water resource availability problems that we have in the world today. Before I begin discussing the HighPlains aquifer, though, I'd like to try to understand a little bit about why we care about groundwater sustainability. Why is it important? And I'd like to begin looking at Costa Rica. And obviously Costa Rica is a country which has very different climate on the eastern and western coasts and the Caribbean and Pacific coasts. This map from 2015 that I found shows how different the precipitation can be from one year to the next, even within the same year. Obviously, there's quite a bit more drought conditions are much more common in Guanacaste than they are in the East Coast, and it's causing some unrest and people demanding access to more water in some of these more stressed regions. And this is certainly a case around the world where we've got water crises. I had the opportunity to visit Cape Town, South Africa during their drought in 2017, kind of right at the peak of their drought. Between 2015 and 2017, they had 3 of the 4 driest years ever on the record, and that's kind of shown with these 3 lower lines here. 2015 is this kind of upper line. This was the start of the drought. 2016, and then 2017 was the driest part of the year. And what resulted from that, I don't know if any of you paid attention in the news or not, but we had a lot of reservoirs that were drained. The reservoirs, for the most part, the water supply in Cape Town comes from precipitation that they capture in reservoirs up in the mountains. Reservoirs and estuaries and lakes all drained during this time period. And there was kind of extensive warnings that they were approaching day 0, the day when there would be no water available for anybody. And these signs were all over the place, telling people to turn off water faucets when they wash their hands, trying not to waste any water. This was actually a sign in the airport in Cape Town. And there were signs on the streets warning people how much water they each had to use every day, or there would be no water left. One of the reasons I was in Cape Town during that time period is because they were looking to transition to groundwater supply, and they were encouraging businesses and wealthier individuals to drill their own wells to tap into the groundwater supply. And it was really kind of a drill baby drill sort of mentality where groundwater is going to be the solution to the problem. But there was not a whole lot of consideration for what would happen once the crisis had passed and everybody was suddenly reliant on the groundwater supply, and then what would be the long-term effects of all of that pumping on the groundwater. And kind of this concept of groundwater sustainability and how to define safe yield is something that has been written about quite extensively in the literature, and we can go through and try to define what safe yield might be in a number of different ways. But people have looked at maybe what we want to do is maximize the quantity of water withdrawn, or maybe we want to look at how much water we can withdraw from an aquifer at a rate that is no longer economically feasible. Or maybe more broadly, and this is kind of a nice definition, I think, that was put out by Todd in 1959, that the amount of water which can be withdrawn from a groundwater basin without producing some undesired result. And obviously, we're starting to incorporate economics in the definition from 1923. The definition from 1959 is really, it's really ambiguous. What is this undesired result? It can be defined differently in different basins. John Bredehoeft has written quite extensively on this misconception of safe development, and a lot of times people have said, well, as long as the amount of water that we're pulling out of the ground is the same as the amount of water that's recharging, then we'll be okay. We're not going to have any real effect on the groundwater system. But the truth is that we also have to keep in mind that when we're pulling out water somewhere along the groundwater flow path, that we're short-circuiting some discharge point further down the flow path. And so to be truly sustainable, Ali and Leek put together a fairly comprehensive definition that says the development and use of groundwater is such that it must be in a manner that can be maintained for an infinite time without causing any unacceptable environmental, economic, or social consequences. And this definition really relies on kind of what the values of a local area are. You know, what are the acceptable environmental consequences of pumping groundwater? Does it matter if we completely drain a nearby lake? Or is there some social consequence of our actions? And so finally, the knowledge that we get about groundwater sustainability has to be founded on some understanding of how much groundwater is actually there, how much water is available. And how do we determine how much groundwater is available? Well, we need to use a lot of different types of data. We need to try to characterize the aquifer system. We need to know something about the water levels. We need to know the geology. We need to know what the water quality is, how that's changing over time. We need to know how much water is being used. We need to know how much recharge is going into an aquifer, and that's not a very simple thing to calculate or determine. There's extensive literature on just trying to determine how much recharge is going into aquifers around the world. To do that, we often need to know something about the evapotranspiration. We need to know what the groundwater surface water interaction is like in the area. How much groundwater is discharging into the surface water? How much surface water is recharging the groundwater? Obviously, climate makes the difference. Regulatory and legal considerations also matter. What are the conditions that are encouraging people to pump out of the groundwater? What are conditions that are encouraging people to conserve water? All of that sort of thing. All of these things, especially all of these over here on the left-hand side, are data that we're going to put together and try to put together groundwater surface water models and come up with some sort of analysis. And in my talk today, a lot of what I focus on in my work is trying to characterize the aquifer and the geology, try to determine trends and changes in the water levels, where the recharge is occurring and how much recharge is going into the system, and using that information to inform the groundwater surface water models, and then eventually taking that the next step into informing policy and actions of individuals who use the water. Okay, so let's take a step for a moment now and move to the HighPlains Aquifer in the United States of America. And my first question, without showing you a map of the HighPlains Aquifer, giving you any additional information about the aquifer, is to ask you exactly how big is the HighPlains Aquifer? Is it roughly the size of El Salvador, Belize, Costa Rica, Panama, Guatemala, Honduras, or Nicaragua? Kind of think for a minute, put a number in your head of how big you think the HighPlains Aquifer might be. And I've kind of put the area of each of these different countries over here on the side just for reference. And it turns out that the HighPlains Aquifer is roughly 450,000 square kilometers. So if we take all of these countries in Central America, put them together, it turns out that the HighPlains Aquifer is about the size of all of the countries except for El Salvador and Costa Rica. So if we take all of the 5 other countries and put them together, that's how big the HighPlains Aquifer is. And we use the HighPlains Aquifer in the United States of America to irrigate crops, to irrigate corn mostly, but also soybeans and wheat and some other crops. And the amount of area that we irrigate is about 58,000 acres, sorry, about 58,000 square kilometers. So that's just a little bit bigger than the size of Costa Rica. So that's the amount of land that we're irrigating and producing crops from the using water from the High Plains Aquifer. So it's not an insignificant aquifer. It's one of the largest aquifers in the world. And it turns out that it's also nearing the end of its lifespan. We've been pumping water out of the High Plains Aquifer at an unsustainable rate since the 1950s. And as a result of that, the water levels have dropped precipitously. And in a lot of areas, we're no longer able to use the water from the aquifer for irrigation. And this is not a new problem. This is something that people have realized since the 1970s was going to happen at some point. So that makes the High Plains Aquifer a very good case study for showing kind of what not to do when trying to manage an aquifer system. So as I said, the High Plains Aquifer is one of the largest aquifer systems in the world. It stretches from South Dakota in the north down through Texas in the south, so kind of right in the middle part of the United States. It's in parts of 7 different states, and it accounts for over 31% of all of the groundwater withdrawals all across the United States. And this is an area where the landscapes are changing quite a bit. Over 70% of the native prairie, the native plants are gone. There's a lot of changing agricultural practices right now, so the land uses are changing. There's a large degradation of water availability, both the quantity and the quality, due to land use and over-allocation of the water supply. There's a lot of oil field development, especially in this part of the landscape. And in those areas, they're using water from the High Plains Aquifer for that development. We're also getting a lot of extreme events in this region. There's droughts and floods are becoming much more common with climate change. And before I leave this slide, I just want to take a minute to point out the satellite picture over here on the lower left-hand corner of the slide. And you can see these circles, and these circles are what we call irrigation circles or center pivot circles. And they're not insignificant in size. Just to give you an idea of scale, this particular circle is a mile across, or 1,600 meters across. So there is a big sprinkler system that goes around a circle here, and that circle, there's about 800 meters of pipe above the landscape that goes around in a circle. And I've got a picture of what that looks like here coming up in a few slides. These smaller circles, the pipes are about 400 meters long. Just a little bit more about the High Plains Aquifer, the geology of the formation. This is kind of a formation that has formed over the past several million years as the Rocky Mountains to the west have shed sediments and resulted in kind of an uplifting of the nearby landscape. So we get a lot of sediments coming out from streams from the Rocky Mountains, very alluvial, and as the streams come out and wash across the landscape, you start to see the sediments filling in these river valleys and eventually covering most of the High Plains area. The land use across the region, and you can see in this picture, the blue areas are rangeland. So this is areas where, for the most part, people are raising cattle. And then the red areas are the areas where we're irrigating agriculture. And you can see from this picture that over across the whole landscape, the irrigated area is, it's only 11% of the total land area, but we're using so much water across that small portion of the landscape that it's causing water levels to decline precipitously, and in many of those areas, irrigation is no longer sustainable or soon will not be a viable option. The climate of the High Plains region, it's semi-arid, so probably more similar to Guanacaste in Costa Rica. The western portion is very dry. We get less than 400 millimeters of rain per year. But as you move east, generally precipitation starts to increase as you move away from the rain shadow of the Rocky Mountains, and mean annual rainfall will exceed 800 millimeters per year in the very easternmost portions of the high plains. It's a very continental climate, so we're very dependent on storm tracks in this region. It gets very warm in the summer, very cool in the winter. Temperatures are much warmer in the south than in the north year-round. And in general, across the whole region, evaporation rates are going to exceed precipitation rates. This region is also affected quite a bit by dramatic changes in climate from year to year and very severe droughts. Some of you may have heard of the 1930s drought known as the Dust Bowl. The Dust Bowl was centered in the High Plains region. This was before there was any real realization of how much water was underground in the area. And kind of can take a look at this area where we've got the most severe dust storm damage from the Dust Bowl and kind of look at where the High Plains Aquifer is. You can see that basically this is an area where the Dust Bowl and the High Plains Aquifer are can pretty much be overlain right on top of each other. With the High Plains Aquifer underlaying this area with such dramatic changes in climate from year to year, having availability and access to the water would be a great boon for farmers and others trying to stabilize the landscape and maintain their livelihood from year to year during drought conditions. Of course, during the 1930s and 1940s, there was no real understanding of how much water was underneath people's feet in this region, or if there was no real way to access the water. It was too expensive to put in to put in wells and pump that water out of the ground. So two things happened in the 1940s and 50s that changed the dynamics considerably. In the 1940s, the technology to pump water out of the ground became significantly cheaper, and in the 1950s, an inventor and farmer in Colorado patented and sold the patent for a center pivot irrigation system to a manufacturer. Shortly after that, a drought returned, and farmers across the region suddenly had a mechanism to try to keep their crops from drying up and protect their profits during the drought seasons. And this is just a picture showing kind of the end of one of those large center pivot systems. In Kansas and in much of this region, farmers have to apply for a water right in order to take water out of the ground. But when they do that, that water becomes something of their property. And this diagram just shows you, this is for one county in Kansas, but it's representative of the whole region. And you can see that over the 1940s, very few people had applied for water rights. A few started applying after that drought in the 1950s, but then it really took off in the 1960s and 1970s. And sometime in the 1970s is when we started to realize that we were taking too much water out of the ground. And so by the 1980s, new development in the region effectively ended. And so although we haven't really curtailed how much water we're using in that time, we haven't added to the problems to any large degree. So the declines were already evident in the 1960s, and you can pretty much pick up the New York Times any given year, and there will be an article such as this. There's articles that show up in National Geographic quite periodically talking about the High Plains Aquifer as well, how much water has been pumped and is gone. And there's one particular farmer, and this is in that same county where that diagram I was showing you just a minute ago. And when they started pumping water out of the ground back in the 1960s, they were able to get over 6,400 liters per minute out of the ground. today the water levels have dropped so much that that same well is only able to get 1,200 liters per minute. Vast stretches of farmland no longer support irrigation, and many areas it's already gone dry. And the thing is that for the most part, and this is becoming increasingly clear through my research, as the groundwater runs out, it's effectively gone. There's no significant recharge across large areas of this landscape. So kind of keep that in mind in the back of your head. Some of the effects of this groundwater pumping are streams have been disappearing. This is the Arkansas River channel in Larned, Kansas. And you can see that it's completely dry. It's one of the navigable rivers in Kansas, but it's only navigable by a four-wheeler. To give you an idea of what's happened to the streams, this is a stream here in western Kansas along the Arkansas River. This is a stream gauging station, and you can see that before we had a lot of pumping, we had several very high flow events, but in general there was quite a bit of daily mean discharge. But after groundwater pumping, there's significantly less water. All of the large peaks are gone, and we can move downstream to Great Bend, Kansas, and that's located right about here. And that's this black line. You can see that although flow rates had decreased quite a bit over this reach of the river, even when there were high flow events, so clearly this was a losing stretch of river. The amount of flow in this area is still diminished quite a bit from what it was before. And so from 1961 to 1994, we've lost a lot of stream flow in western Kansas. This is fairly typical of what's been seen across the HighPlains aquifer. And one of the key conclusions that has come out of this is that despite the relatively thick saturated interval, it's likely that large-scale irrigation withdrawals will not be sustainable beyond the current decade in the vicinity of this Haskell site, this Haskell area. And this was actually causing quite a bit of strife. There's been several lawsuits have been filed in the area, and people have started to shut off other wells as a result of the groundwater declines. And you can see in this diagram here across the HighPlains aquifer what these declines look like. In some areas, we've lost more than 45 meters of saturated thickness. In some areas, there's actually increased water. So the water table is increasing, and that's mostly because we've got surface water irrigation, leaky canals that are taking stream flow from further upstream and depositing it downstream through these leaky canals and whatnot. So why do we have this problem? I mean, we've known since the 1960s and 1970s that the groundwater is declining. It's still declining. We're still looking at sites where water use is not going to be sustainable. Why is this? Well, there's multiple issues, and my dad was a pilot, and it's kind of like an airplane. There's typically no single reason for an airplane crash. It's typically several different issues that come together and cause a crash. It's the same thing here. We've got multiple issues that are causing the groundwater declines. First issue we have is that surface and groundwater resources are initially treated as separate resources, and in fact, to a degree, they still are. They're not regulated in the same way across most of this region. There's also a use it or lose it policy. So if you're given a water right, it's your property, but you have to keep using all of the water that you've been allocated. Otherwise, they're going to take your water right away and give it to somebody else. So even if it's a really wet year and you don't need to use the water, the incentive is there for you to use the water. There's continued development pressures. As I said, this is an area where there's a lot of oil and gas exploration going on. People are trying to use that water, but also as we're seeing the water tables drop, the area is also becoming affected more the area is becoming affected more and more by significant droughts, which are causing more people to want to use more water. This is also a transboundary aquifer. So it's not like we're going across different national boundaries, but it does go across different state boundaries. And so each different state has their own rules and regulations, and to a degree, it kind of winds up acting somewhat like its own individual nation. They have to come up with agreements between these different states. There's a lot of different irrigation and groundwater management districts, and all of these areas have different laws, regulations, and practices. All of these areas collect data differently. There's different frequencies of how often data are collected. People collect data different methods. Different people are responsible for collecting the data. In some places, it's the U.S. government. In some places, it's a state agency. In some places, it's a local groundwater management district. So the result of this is that there's a real big mishmash of different data available, and it's not very easy to pull it all together into one comprehensive picture. Okay, so the next question really that I have that I'm trying to answer is, how do we extend the aquifer lifespan? And the HighPlains aquifer, it's very clear that we need to reduce water use, but how do we get to this point? It's a very late stage of the development cycle, as I said, so it's kind of a bellwether for other aquifers. We've made many bad decisions here. There's been years of inaction, and the longer that we've waited to make any actions, the harder those actions become, and the consequences of not acting become more severe as well. Across the region, as I'll talk about in the rest of my talk today, we need more data. I'll talk about what kind of data are needed, but we also need to integrate science and policy better, and we need to have buy-in from landowners and water right holders. Ultimately, what's needed is action. We're kind of past the point where we need to be talking about the issue, and we're at the point where things need to be done. Okay, so when I talk about data, I want to talk about how much water there is and where the recharge is. These are kind of the two key components. If we don't have a very good handle on how much water is there, we don't know how much we can use. If we don't know how much recharge there is, we don't know how much we can safely use. In Kansas, to try to understand how much water is there, they've gone to collecting annual point water level measurements, and they're measuring approximately 2,200 wells every January. So this is by no means all of the wells, but this is kind of a statistically significant number of wells that they've identified, and they base this entirely on a two-dimensional land surface. So this model, the statistical model, is completely ignoring the aquifer geometry. And this is important because there's a lot of other factors that are going to influence water level measurements, such as how long the well screens are, which aquifer it's screened in. It turns out, we think of this HighPlains aquifer as this, one big bathtub sort of a thing, but really it's a lot of different compartments within the same stratigraphic unit. So if you think of a stream going across the landscape and depositing sediments, you're going to have areas where there's really high permeability gravels and other areas where there's lower permeability silts and clays, and it's the same thing here. This is a very large area, as I said. It's roughly the size of most of Central America, and it's very difficult to collect measurements across such a large area. It's a very low population area, and so there's not a lot of resources available to go out and collect the measurements that are needed. In general, there are very few continuous water level measurements being made in dedicated monitoring wells. This is slowly improving, but it's not improving nearly fast enough. Just to kind of give you an idea of how the saturated thickness has changed from 1996 to 2018 or so. I've got this diagram here, and you can see these darker reds are going to be a decrease in saturated thickness of over 25%. In some of these blue areas, we'll have some small increases. So you can kind of get an idea of where the biggest problems are, at least in the state of Kansas, and they're going to be in the southwestern part of the state. Again, this is that area that was closest to the center of the Dust Bowl. But there's also some problems up here in the central part of the state as well, central and northern part of the state. Kind of an actual picture of what this looked like from before we started irrigating to today. And you can see that there are areas where over 60% of the saturated thickness is completely gone, and other areas where we've even lost 30 to 45% or more. Most of these increases are in areas where the aquifer is very thin and people are not using it to any large extent. So the question of how often do we measure the water level measurements often comes up. And the frequency of the observations and the timing of the observations are really pretty critical. This is a monitoring well that we've got out in western Kansas in a county called Thomas County. And I've got the annual water level measurements put on here. This is a well that's part of the annual water level measuring program. And from one year to the next, you can see that there is approximately a half a meter change in water levels, and it looks like there's no real difference in the actual water level over a 3-year time period. And that looks great from the perspective of the annual water level measuring program. Okay. But if we take a few more measurements over the course of a year, so instead of going out every January, we'll go out over the course of the year, and you can see that there's quite a few more, there's a much larger variation in the water level over the course of this year. And in fact, it's closer to about 1.5 meters change in water level from the lowest to the highest level. So clearly, this measurement that we're taking in January is not showing the aquifer at its highest level after we've been pumping it and pumping water out of the ground. But it's also not at its lowest level. So what is the meaning of this January measurement? If we overlay that with pressure transducer measurements, so this is a much more continuous, complete record of the water levels, you can see that the water level does indeed change by several meters per year. And in fact, over the course of an individual week, you can see that the water level measurement will actually vary by up to 15 to 30 centimeters. So that's not an insignificant amount. And what's causing that? Well, it turns out that barometric pressure changes are affecting the load in the aquifer, the pressure load on the aquifer to such a degree that it's affecting the water level measurements differently in the well versus the aquifer. And so we've got this change in water level of up to 30 centimeters that has no bearing whatsoever on the actual amount of water in the aquifer. And so depending on when we go out for this annual water level measurement over the course of a week, we could see that we've got an increase in water level measurements, a decrease in water level measurements, or maybe no change at all. And with over 1.67 meters, so almost 1.7 meters of annual water level variation, and ignoring this barometric effect is equivalent to an error of 20% of the annual drawdown. So that's not insignificant at all. So when we go out to measure these annual or point water level measurements can matter quite a bit depending on what the geometry of the aquifer is. So what do the water level declines look like? So this is back in that Haskell County in southwest Kansas where we've had a lot of issues. And in pre-development times, the depth to water level was only about 20 meters below the ground surface. By 2008, when I moved to Kansas, just before I moved to Kansas, the water levels had declined almost to the bottom of this kind of upper sand unit. So the gravels are this kind of beigey color. The sands are kind of a yellow. And then we get into the silts and clays, and they're these kind of darker colors down here. As we move on from year to year, you can see that by 2014, this particular well was at the very bottom of this upper sand unit, about to hit these this very thick section of clays and gravels. So even though we've got approximately 40 meters of saturated thickness here, it's not all usable. So you can see that the rate of decline has changed over this time period as well. From the first couple of years, we had a fairly slow rate of decline, but then kind of through time, it's decreased quite a bit more. But by 2014, it actually kind of leveled off a little bit, and that was the result of a lawsuit and injunction that stopped people from pumping in this area because the water levels were declining so quickly. So although it may look like there is almost 40 meters of saturated thickness left to pump water from in this portion of the aquifer, the practical saturated thickness, the amount of aquifer that is actually available to pump water out of, to readily pump water out of, is closer to 10 meters thick. So this is an area where the water level declines are very critical at this point in time. So with so much water being removed from the aquifer, it's also important to understand how much water is returning to the aquifer and where that water is returning to the aquifer. Okay, so we've got two different types of recharge. We can have diffuse recharge pathways, and I was fairly confident that this would be the primary source of recharge to the HighPlains aquifer. And in a diffuse recharge, it's basically you've got a fairly similar amount of recharge to an aquifer across a large area. You can also have focused recharge, so this would be cracks in the ground, macropores, larger pores where water can perhaps move more quickly. You could have areas where the ground is wet for longer periods of time, such as beneath an irrigated field, or maybe a pond or a lake or something like that. Or you could have recharge through a stream bed. Clearly, this is an area, although this is a dry stream bed. In the past, there was a losing stream reach in this area, and any water that might find its way into the stream reach would likely have an easy pathway down into the aquifer. So I've been studying this using scientific coring. So we've got two different methods. One is a hollow stem auger here on the left, and then a rotosonic rig over on the right. And so we use the hollow stem auger through that large, thick, unsaturated zone so we can pull the core out. And it does a very good job of collecting core in the unsaturated zone. But once we get into the saturated zone, it doesn't do as good a job recovering the core. So we switch to a rotosonic rig, which can collect, we can get much higher recovery rates in the core. Okay, so the first area that I'm going to look at for recharge and try to determine how much water is returning to the aquifer are through these playas. And playas are a fairly predominant feature across the HighPlains region. There are these areas in blue, and it's not entirely clear how they formed, but they're very common features, and they're fairly small closed basins. Water, during large rain events, water will flow into them, they'll stay ponded for a while, and then eventually dry up. And so I'll take a look at recharge rates through this particular playa. This is located in west central Kansas, and I'm using the chloride mass balance method to try to determine what the recharge rates are. And you can see before inundation, before the playa filled with water, it had been dry for several years. You see kind of this interesting relationship in the amount of chloride. And it turns out that as water is removed by plants, chloride is left behind. And so we get this peak at or around the base of the root zone. And then it kind of, in this case, it's gradually increasing here as well. And so you can see this reflected as well in the gravimetric water content. So where the plants are pulling a lot of water out of the ground, the gravimetric water content also decreases quite a bit. If we look again at that same location after the playa was inundated, that peak is gone, and the chloride has been pushed down through the unsaturated zone towards the vadose zone. We can compare that with an area nearby where in the part of the landscape that we call the interplaya, or not the playa. And you can see this very large chloride peak, which is several orders of magnitude higher, indicating a much lower rate of recharge. We can actually calculate that over to a flux, and you can see that the flux rates through the playa region are significantly higher than they are in the interplaya. We're currently working to add chlorine-36 age dates to this to try to get a better feel for how much, for how old the water is actually in this region, and get a better kind of a second verification on the groundwater flux rates, the recharge flux rates. We don't just have geochemical evidence of recharge, we also have stratigraphic evidence. So there's physical evidence of this recharge. And just for scale, I'd like to show you that there's this truck driving through here, and this is the playa itself. And my colleague Bill Johnson has been working on playas for years, and happened to across this location where they were excavating for a completely different purpose, but he was able to get into the middle of the playa during the excavation and take a look and see what the stratigraphy looked like. And this is what the inside of the playa looks like. You can see this darker soil up here at the top. That's showing us roughly where the playa, the hydric soils of the playas are. There's also kind of these fingers down in here, and some of these whiter sediments, and these white sediments are carbonates. And they're forming as the water is moving through the system. And it's not just moving in a vertical direction, but you can see kind of over here at the edge of the playa, it's also moving off and away from the playa. So we're getting water that's kind of spilling over the edge of the playa and out and down. Okay, so the playas are providing recharge to the aquifer, but they're not providing enough to compensate for the amount of water that's being withdrawn every year. And this is data from across the High Plains region that was predominantly the southern High Plains region that was compiled by the USGS. And you can see that in general, recharge rates through the playas, they've got a fairly large range, but they're relatively high between, for the most part, between 10 and 400 millimeters per year. Which is significantly higher than in rangeland, where recharge rates are on the orders of 20 tenths of a millimeter per year up to maybe 20 millimeters per year. So if playas can't provide all of the recharge that we need to the High Plains aquifer, perhaps we've got more water flowing beneath irrigated fields, and this can provide us the water that we need for recharge. And there's two possible ways that we might have additional recharge through irrigated fields relative to the surrounding landscape. The first is, because these soils are a little bit more wet than the surrounding landscape, they're going to be able to provide there's higher permeability through these sediments. Of course, a wet sediment has a higher permeability because there's less air pockets in it than a unit that's drier. At the same time, if a farmer is putting too much water on the field, then perhaps we can have water that's flowing through the unsaturated zone rather than running off, because this is a fairly low, fairly flat landscape. And one of my students took a look at this, and it turns out, at least in her study, that for the most part, the water that we found in the upper part of the Vados zone was very clearly new water. It was not, we do see several spikes in here that's showing us that we do have some water being pushed down through that Vados zone that's moved beyond the root zone. But at the same time, kind of beneath this pre-development water table, all of the water that we see is very similar to what we see in the groundwater, which is this kind of blue stippled area here. Because the chemistry is so similar, that tells us that the Vados zone has not, we don't have water coming coming through and pushing out the groundwater and recharging into the groundwater. So this is all old water in the vadose zone in this area that's not completely drained out. So we don't have a lot of water flow through this area. In fact, if we look across the whole High Plains region, kind of the recharge rates that we see, the flux rates range between about 17 and 102 millimeters per year. So although that is higher than what we see in the surrounding rangeland or interplaya regions, it is not as much as what we see beneath playas. So one of the last areas that I'm looking at right now is what I call big data. So there's an increasing push in the United States and Canada to put together a lot of disparate sources of data. So we've been collecting data individually in all of these different agencies, and we're starting to put them together into larger databases which are publicly accessible. And I picked a couple of different tracers here that are readily used to identify water that is recharged in the last 50 years. And so this is tritium and chlorofluorocarbons and High Plains aquifer groundwater. The red ones are areas that we detected it. Blue are areas that we didn't. And as we pull this data together, we can see that there are areas where there's a lot of more recent recharge. There's areas where the recharge is much older. And if we can kind of overlay some features like the streams onto this map, we can see how far away our recent groundwater is to some of these features, and see if we can start to identify some of the recharge areas. So I'm using this not only with tritium and CFCs, but also radiocarbonages, different agricultural contaminants, nitrates, pesticides, fertilizers, and all that sort of thing. So just to summarize the data that we've been looking at in the High Plains aquifer, the water used is unsustainable. It's been a known issue for the last 40 years. We have been improving our water availability estimates, both using water levels and recharge. But the question remains, how do we change the water use pattern? And I think to do that, we need to kind of bring science and policy together with action to actually kind of co-create our path forward. It can't just be scientists telling the resource users and the resource managers or policymakers what needs to be done, because there's other realities that they have. And likewise, the resource users can't just keep using things at the status quo. So in Kansas, we have had a few policy changes in the last 10 years or so. And the first was this the removal of the use it or lose it incentive, as well as the establishment of a local enhanced management area. So these local enhanced management areas are areas where, rather than having the government tell people what to do with their property, the local landowners are getting together and realizing, listen, we've got a tragedy of the commons. Everybody is incentivized to use as much water as we can. But if we all get together and agree to reduce how much water we use by the same amount, and then we can maybe actually affect a change. We're also working on playa conservation efforts because these seem to be the largest sources of recharge to the aquifer. But at the same time, a lot of people will farm across them, which causes sedimentation, fills in cracks where water can seep in, and reduces the water holding capacity, which reduces the length of time that they are inundated. So I've been talking a lot about the High Plains aquifer, and how might we be able to apply this to other areas, for instance in Costa Rica or elsewhere. And the big thing is that there was really a poor understanding of how much water was there from the start. So people were using water kind of at will and developing the water as quickly as they could, and they just didn't have the information they needed. So what kind of information do we need? We need to know how much water is there. We need to know what the water levels are. We need to know what the storage characteristics of the aquifer is, the recharge sources and rates. We need to know something about the geology. I'm very interested to know what the chemistry of the aquifer is and something about the recharge characteristics, how old the aquifer is using isotopes. And if there is any water use in the region already, we need to know what that is. If we get to a point where an aquifer is overdeveloped, it is extremely difficult and extremely expensive to curtail later. And the longer you wait to address those issues, the more difficult and the more expensive they become, and the harder it is to make those changes. Very often, there's a lack of both social and political will to make the changes that are necessary. People don't want to change how they're living. Politicians have a very short, at least in the US, have a very short time frame. They're thinking, 4 years or whatever to the next election. They're not thinking of making decisions that can have an impact for the next 10, 20, 30 years. And kind of no matter what, when you're dealing with scarce resources, conflicts are inevitable, and it's much easier to deal with them early and doing a good job from the very beginning. Very clearly, we need to have scientific information in order to inform the public discussion. The data and the decisions that are used are made from those data. They need to be available to the public. The more local control and the local input that we can have, kind of the more buy-in there is to make the changes. The public needs to be engaged. Managers, the resource managers, and the policymakers all need to be engaged by the scientists, but it can't be a one-way street. Science is not the only factor in the discussion, and scientists need to be able to kind of take into account different societal expectations, economics, and environmental concerns as well. Okay, and I'd like to thank you for your time, and I'll take any questions that you might have.
Thank you, Randy, for an excellent talk about the situation of these aquifers in USA. I'm starting worrying about the possibility that something like that can occur in Guanacaste. I hope not. Well, there are some questions here for you, Randy. I am trying to translate them from Spanish to English. The first one is about the safe yield. In Costa Rica, we use 40% of the calculated recharge as a safe yield in order to prevent overexploitation. What do you think about this? This question is from Roberto Ramirez from Senara. Oh, I think you have to turn on your microphone. Okay.
Okay, great. Yeah, so I think that's an excellent, that's the right strategy to take. In the US, when they started developing this aquifer, we didn't have quite the same understanding of how much water is available and how that water would get into the ground that we do today. And there was this idea that it was kind of this limitless supply. And so having a kind of at least a baseline there saying, we're not going to use more than some certain amount of the recharge, I think that's definitely a good place to start. There's certainly, kind of additional considerations as to whether or not that's an appropriate, whether one of the questions later says they use 40% as the calculated of the calculated recharge as your safe yield, and whether or not that's an appropriate number is going to depend on a lot of factors like geology and what sort of impacts using the water might have downstream and down hydraulic gradient. So
there is another question from Rodrigo. He is a student of the geology program, of the undergrad program. Rodrigo asked, have you done any study about the quality of the water being recharged related to agrochemicals or pesticides on farming lands?
That's an excellent question. And it's a very large region. So obviously there's, differences across the region. And in some of the areas, the amount of recharge that is coming through and the length of time it takes for that recharge to get from the surface down to the groundwater, it almost doesn't matter what the water quality is of the recharge. There are some places where we do have some faster flow paths where water is coming through that does have pesticides and nitrates and other agrochemicals in them that do cause some problems. And there are some areas where, I showed that region where there is some surface water irrigation, and some of those streams do pass through Cretaceous age shales, and those Cretaceous age shales provide different elements like uranium and selenium that kind of become evapoconcentrated in the return water that's coming back to the streams and back to the groundwater. So there are some water quality concerns as well.
Oh, thank you. Another question from Daniela says, have you run any kind of economic optimization model to make better location?
Yeah, I haven't. I'm not an economist. There are people that have looked into that. And yeah, so the short answer is that people have looked at that, but it's not something that I've looked at.
Okay. Is the oil exploitation in those states, is it there oil exploitation in those states?
There is oil exploration in Texas, Oklahoma, Colorado, and Kansas. And kind of the most recent, it's been there since the probably the 1930s or so is when they first discovered oil. And the more recent push has been a lot of this fracking and that you hear a lot about. So they're going after kind of tighter units and using quite a bit more water to get at the units.
So in that case, what is the relation of the oil sources with the aquifer, says Arturo? Yeah,
good question. The oil sources are quite a bit deeper than the aquifer. There are places where the aquifer is about 160, 200 meters deep. And the oil, for the most part, tends to be over 1,000 meters below the surface.
Okay, and the last question, I am trying to translate this a difficult question, I think. It is possible to use groundwater by pumping wells, extracting the equivalent amount of the recharge and continuous extracting water from the storage and allow capturing recharge systems to get precipitation from the surface runoff.
That's coming into the aquifer, we should have a balance and everything should work out really well. The problem is that, if we're pulling water out of an aquifer, there's some discharge point further down. And in a country like Costa Rica, that discharge point might be under the ocean, and so there might not be too big of a problem. In a place like Kansas, the discharge point would be a stream or a lake or something. And so if we're capturing the precipitation along that flow path, then we're still preventing it from reaching that endpoint further on. And kind of the further we are from that endpoint, whatever that discharge point might be, the longer it would take to see the impact, but at some point you will still see an impact at that end discharge point.
Well, I think we'll have time to do more questions. Thank you again, Randy, for your excellent talk. Now we have many concerns about the situation, especially in Central America, with the scenarios of climate change and the excess of watering during the rainy season and the droughts that we have during the summer. So thank you again for your time and all your effort to prepare this talk, and hope we can see you in future in more talks or activities like that. Thank you very much.
Thank you very much for having me.